All right, so in the previous chapter and a half, we've been getting an understanding of the structure of different molecules, starting with the Lewis structure, which shows us just the arrangement of atoms in relation to one another, as well as the distribution of electrons in single, double, triple bonds and lone pairs, whatever it may be, depending on the specific molecule that we're looking at. And then we started to look at the true three-dimensional sort of structure shape of these molecules based on the electron groups around the central molecule. Now we'll get a better understanding of what's actually occurring with those bonds. And what we're going to be looking at is the orbitals involved. And when we're actually forming a bond, remember, in a covalent bond, the electrons are shared between those two atoms. So with the bonds being formed, what we're going to see is there's just going to be orbital overlap. So if we look at a couple examples at the bottom here, with something like diatomic hydrogen or diatomic chlorine, we can see the two atoms are just going to overlap. So with hydrogen, we've got the spherical s orbital. Chlorine's got the p orbitals that are kind of dumbbell shaped. But in both cases, we're seeing those orbitals overlap. And then where that overlap is occurring is what we can kind of think of as the bond. That's going to be where the electrons are being shared, essentially. And then we can see the same thing in the middle, where we look at hydrochloric acid, HCl. It's just in this case, we've got an overlap between an s orbital and a p orbital from chlorine. But it's still the same idea. We've got that overlap, so we're going to be sharing electrons. We're going to be creating that covalent bond. And then with this, remember, the reason we're going to be forming bonds is ultimately to get to a more stable configuration in terms of the electrons. To get to a lower energy, everything in the universe is moving towards low energy. So if we think about just two hydrogen atoms, and they're completely separate from one another, they're gonna have some energy associated with them. As we take those two atoms and start to bring them closer and closer together, we can get those orbitals to overlap, and then again, that's going to be where we actually start to form this bond. But when we start to have those orbitals overlap, what we're going to see is the energy is going to start to decrease, because with this process, what we're going to see is the positive nucleus or nuclei of these atoms are going to reduce the repulsion from just the electron-electron repulsion there. So it's going to be a little bit more energetically favorable. And we're going to see that continue to occur until we get to a sort of an optimal distance between those two nuclei. Because once we get past it, in this case, once we bring these two hydrogen atoms closer than about 3/4 of an angstrom, what we're going to see is now we're going to start to have repulsion between those two nuclei. And that's going to be why we start to see the energy drastically increase. So with this bonding, we need the orbitals to overlap. So we can't have them super far apart so that there's no overlap, but we also can't have them extremely close together, because then those nuclei are going to repel each other, and it's just not going to be a favorable state in terms of the energy. But with the three-dimensional geometries we were just looking at, we can have things like tetrahedral, trigonal bipyramidal, octahedral, and those are going to be a little bit difficult to understand if we think about just traditional orbitals. So we've got an S is just going to be sort of that sphere shaped. The P, we've got PX, PY, PZ, so just on those different axes, because we're going to have three orbitals in the P subshell, kind of dumbbell shaped. But what we're going to start to look at now is hybridized orbitals. So instead of just having S or P, we're going to have kind of an average of those two. And if we think about beryllium at first, so beryllium atomic number of 4, it's going to have 4 electrons, 1 s2, 2 s2. With the beryllium atom, it doesn't have any unpaired electrons. So none of these orbitals are singularly occupied. It's not going to really be able to share electrons in this way. So it's not going to be able to form bonds, basically. So what we're going to see in this case is we're going to promote one of these 2s electrons into the 2p orbital. And now we'll have two singly occupied orbitals. We're going to be able to form 2 bonds in that case. But when we do this, as I was saying, we have hybridized orbitals. What that's going to result in is, instead of an s orbital and a p orbital, now we're going to wind up with 2 hybrid orbitals. And we're going to consider them, in this case, sp, because we've taken one s, we've taken one p. So s and p is just what we're referring to the hybrid orbitals as in this case. And then with these orbitals, we can see why then beryllium fluoride BeF2. Why that would form is because we've got these two orbitals available. That one electron in the 1s, one of the sp hybrid orbitals, can share with fluorine. So if we think about fluorine, it's going to have all of the 2p orbital, or two of the 2p orbitals completely filled, and then the third will be partially occupied. So now we can have those orbitals overlap. We can share those electrons, form one of the bonds, and then the same thing on the other side to form BeF2. And with this, we've got two hybridized orbitals. Again, that's why it's just sp, because we've got two electron groups here. And that's why the best way for these bonds to spread out is just going to be 180 degrees. Because remember, these electrons still want to minimize the repulsion between each other. So they want to be as far apart from each other as they can. And in the case of two electron groups, that's going to be a linear structure. So that's why we would see the bond overlap actually occur like this, so that we can get that linear structure there. But when we think about the orbital filling diagram here, this is what we would actually kind of want to consider beryllium as, and in the lead up to BeF2, because again, we took one of those 2s electrons and promoted it to 2p. So now we've got this hybridized orbital. And with it, this is going to be a lower energy than 2p, but it's going to be a higher energy than the 1s. And that's why you can kind of think of it as an average almost, because it's going to be in between them. And then if we go back for a second to the shape, you can kind of think of it as the average of those two. So again, spherical for S, dumbbell for P, but now with the hybrid sp orbitals, we kind of have that dumbbell shape, but one of these lobes is going to be much larger than the other. And that's why when we get to the overlap, we can actually see that occurring now. But if we continue with this concept with boron, so we just added a fifth electron, we're ignoring the 1s here. What we're going to see with boron, and the reason boron can form 3 bonds, so if we think about BF3, is going to be because instead of just this single unpaired electron, we're going to take one of these 2s electrons, promote it, and then remember with Hund's rule, we always fill in an unoccupied orbital, so that's why we're not just going to double up in this first 2p orbital. But we promote it, and now we've got hybridized orbitals. In this case, though, we've got 3 hybridized orbitals because we really filled up. We've got 2 of the 2p orbitals being used here. So that's why in the case of the hybridization, we would refer to this as sp2 hybridization, because we've got 3 of those orbitals, 1s, 2 of the p's, giving us 3 in total. And that's why when we look at something like BF3, the reason it's going to ultimately give us the trigonal planar shape is because once we've hybridized these 3 orbitals, now the best way for them to spread out is just going to be 120 degrees apart. And if this is our central bromine or central boron in the center, now these orbitals would be able to overlap with, similar to the previous one, overlap with the fluorine orbital or whatever that other atom's going to be. And that's going to be where we'll actually be able to form that bond. And with it, again, these orbitals are going to be same energy as each other. So sp2, lower than 2p, higher than 1s. But these 3 orbitals, just like when we think about the 3 2p orbitals, we group them together because they're degenerate. They're the same energy. We see the same thing once we hybridize these orbitals. Now all 3 of these sp2 orbitals are degenerate, meaning that they're going to be equal energy as one another. And we can continue with this idea if we go with carbon next. I don't know why this keeps happening, but there's some animation on this previous slide for some reason that just skips it forward. But we see the same idea where we're just now promoting this 2s orbital. We wind up with 4 singly occupied orbitals, and that's why the hybridization would be sp3 there. And then again, with it, when we've got 4 orbitals now, 1s, 3 of them p, but they're hybridized. That's why we refer to them as sp3 now. We can start to see why this is, again, going to be that tetrahedral structure. The best way for these orbitals to spread out is just going to be 109.5 degrees, and that gives us sort of the triangle base at the bottom, raised up in the middle for that central atom, and then the 4th orbital just coming off the top there. And then once we expand the octet, now we're going to have to do kind of the same thing, but we're going to have to include the d orbitals. So in this case, this would be the configuration for something like this would be for phosphorus, actually, because we're looking at 3s and 3p, and we're halfway through that 3p orbital. But now if we're going to exceed the octet, what we're going to do is take one of those s electrons, promote it all the way to the 3d block. And now we've got 5 singly occupied electrons, or 5 singly occupied orbitals, excuse me. So when we hybridize them, we want to make sure that we're accounting for all 5. So that's why we're listing it as sp3d. Those are going to be our 5 orbitals, but we've hybridized them, and that's why we're kind of grouping them together here. And this is going to give us the trigonal bipyramidal shape that we see. So we've got the 3 equatorial around the middle, and then the 2 axial positions at the top and the bottom. And it would be the same idea if we've got sp3d2. It's just in this case, now we've promoted a second electron, and that's why we've got the second d orbital being hybridized as well. So that's why we've got 6 of them here. But with these hybridized orbitals, if we know the electron domains around that central atom, we can pretty easily determine what the hybridization has to be, because the number of electron domains is going to be equal to the number of orbitals that we hybridized. So with the first one here, rather, BeF2 or something like mercury chloride, we've got 2 different electron domains. So that's why we just have sp. We've taken 1 s orbital, we've taken 1 p orbital and hybridized them. That's why we've got the linear structure. Now for 3 electron domains, we've got 1 s and then 2 p orbitals that are hybridized. Tetrahedral, just the additional, that final p orbital. And then as we get into trigonal bipyramidal and octahedral, we've got the d orbitals being involved. So we've got 6 hybridized orbitals in octahedral, 1 s, 3p giving us 4, and then the 5th and the 6th are going to come from those hybridized d orbitals there. So with this, the hybridization is just going to match the type of electron geometry we see here. And if we look at a couple examples, I'm actually going to go with B first, just because it's going to be a little bit quicker. But for this one, we don't even need to draw the structure, really. What it's ultimately going to be is a sulfur in the middle, 6 bonded fluorines, and then no lone pairs on that sulfur. So since we've got 6 electron groups, we need to have 6 hybridized orbitals, 1s, 3p, d2, gives us our 6 orbitals there. And then with the other one, sulfite, so ITE ending, because we just have 3 oxygens rather than 4, which we would have for sulfate. What we're going to see is that one of these oxygens in the Lewis structure is going to be double bonded, whereas the other 2 are going to be single. But because this structure is going to have 26 electrons, we're also going to put a lone pair on that sulfur there. And then to make the structure complete, we put brackets around it, put the -2 charge there. But in this case, we've got 3 bonded atoms as well as 1 lone pair on that sulfur. So we've got 4 electron domains. We need to have 4 hybridized orbitals. So we would have sp3 in this case. So if we're trying to determine what type of hybridization is on an atom, we just need to know the electron geometry. And then depending on how many electron groups, that's how many hybridized orbitals that we're going to need as well. And with this, we're going to see that the bonding that occurs, or the way that the orbitals overlap, can actually be different, and that's going to give us 2 different types of bonding here. So with the first one, and these are always going to be our single bonds, is going to be sigma. And when I say single bonds, it's going to be something like hydrogen, 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 chlorine, and hydrochloric acid, or the single bond in chlorine molecule, the diatomic. Because in this case, what we're going to see is that the overlap between those orbitals is going to be what's known as head-to-head. So they're basically going to be pointed at each other. Can't really see it as well with the hydrogen, just because of the sphere doesn't really have a direction to it as much. But with the other two, with the p orbitals now, we can see, especially with the chlorine molecule, head to head, just meaning that the orbitals themselves are going to be pointed at each other. So this is going to be the type of bond that forms when we've got just a single bond, but also when we've got a double or a triple bond. This will be the first bond that forms, you can kind of think about. And then the double and the triple bonds, what we're going to see are known as pi bonds. So in something that has a double bond, for instance, we're going to have a pi bond occurs, and instead of head-to-head overlap, so instead of the p orbitals, for instance, pointing right at each other, we're going to have these basically run parallel almost, and then we're going to have the overlap side to side. So if we think about the electron density with a sigma bond, it's going to be between those two atoms. So you can kind of think of it as the inner nuclear axis, right between those two nuclei. Whereas with the pi bonds, we're going to see it's going to be above that or below it, if you kind of look at it this way. And like I was mentioning, with the single bonds, so hydrogen, that's always going to be a sigma bond, because that's going to be a stronger interaction. So it's going to lower the energy more, just because the overlap is going to be preferred there. But when we've got something like C2H4 or the nitrogen molecule, where we've got multiple bonds, we're still going to have one of those sigma bonds. But now in the case of a double bond, that second bond would be a pi bond. Or in the case of a triple bond, we'll still have one sigma bond with the head-to-head overlap. But then the second and the third bond would be those pi bonds, where we've got the side-to-side. So if we look at something like formaldehyde here, we can look at the central carbon, see that we've got 3 bonded atoms and no lone pairs. So we've got 3 electron domains. That's why we're going to have sp2 hybridization here. So when we look at the actual the orbital overlap that's occurring, we can see with the carbon, again, sp2 hybridization. So we've got those 3 orbitals, one of them going to the hydrogen, one of them overlapping with the second hydrogen, and then the third is overlapping with oxygen to give us those sigma bonds. But in this case, we've got a double bond. So what we're going to see is we've got the pi overlap between those 2 atoms as well. And with this, you'll notice the pi bonds. These are going to be unhybridized orbitals, whereas the sigma bonds will be hybridized there. And the reason we have this pi, or we have this unhybridized p orbital, is just because we only have sp2 hybridization. So remember, with carbon, we've got 2s, and then we've got 3 orbitals in the 2p. So we hybridize the 2s orbital with 2 of those p orbitals, but we still have the third p orbital unhybridized, and that's why we're able to have this pi overlap here. That's why we're able to have that double bond between the carbon and the oxygen. And then the same thing if we look at something like acetylene. So 2 carbons triple bonded with a hydrogen on each side. So in this case, we've got two bonded atoms, and each carbon we can treat as pretty much identical. So if we just focus on the one on the left, we've got 2 bonded atoms. So we've got sp hybridization, because we also don't have any lone pairs there. So we've got sp hybridization. So we've got one of those orbitals going to hydrogen, the other orbital overlapping with the carbon. So that's going to give us our sigma bond. But then we've got these 2 unhybridized p orbitals in each case. And what we're going to see is that those are actually going to wind up overlapping to give us a second bond, and then give us a third bond as well. So with the multiple bonds, one of those is always going to be a sigma bond. The rest of them will be the pi bonds. And then with this, we can use this concept to get a better understanding of resonance. Because if we look at something like nitrate, any of these structures would be acceptable for the Lewis structure, because it uses the correct number of electrons, 24 in total. And then it fills the valence shell of all of these atoms. Remember, nitrogen's in the second period. That's why we can't exceed the octet here. Can't expand that octet for the second row and above. But with it, we can have this double bond in any of these positions. So we could have it going to the top, we could have it going left, we could have it going right. And there's really no difference between those structures. But we know from our previous discussion that none of these individually truly represent the molecule there. And we're going to be able to get an understanding of why that is because of these overlaps, because of our orbitals, I should say. Because if we think about what we just have with one of those Lewis structures, go back for a second, on this nitrogen, 3 bonded atoms, no lone pairs. So this nitrogen is going to be sp2 hybridized. Whereas the oxygen with the double bond is going to be the same. So it's kind of showing that p orbital overlap there. But we actually have p orbitals on all of these oxygens. So when we see the true structure, we see overlap between all of those p orbitals. And that's why we're going to refer to these electrons in resonance structures as delocalized. Because we don't actually just have them being shared between this central nitrogen and one of these oxygen. We have them delocalized throughout this entire p orbital overlap there. And that's going to be why, if we go back for a second one more time, rather than thinking of this as 2 single bonds and 1 double, since it's delocalized, it's really spread throughout. We've got 4 bonds in total. If you kind of think of it as 2 double, or 1 double, 2 single, we've got 4 bonds in total around that nitrogen. So what we're going to see is, rather than actually having specific positions for 2 single bonds and 1 double bond, we're going to kind of split those 4 bonds over these 3 connections. So you can kind of think of each of these bonds as being like 1 and 1/3, rather than 1, 1, and 2. And then similarly, when we look at benzene, we're going to see a similar structure. So with benzene, we're going to have 6 carbons in a ring, and then we have the 1 hydrogen coming off of each of those. So with it, we'll have sp2 hybridization on these carbons because they're bonded to 2 other carbons as well as the hydrogen. So they've got 3 bonded atoms. And with the structure, we typically will either represent it with repeating double and single bonds, but we could start with that double bond on top and then have it go back and forth, or we could start on the bottom and go back and forth. And again, there's really no reason for one over the other. So a lot of the times we represent it with just the circle in the middle. And then remember, with these structures here, this is sort of the organic chemistry way of showing it. Each of these corners just represents a carbon. And then carbon typically wants 4 bonds. So anything that's not, any carbon that's not fully filled is just assumed to have hydrogens coming off of it. So for all of these carbons, if you look in the Lewis structure, or in the line structure up here, each of them has a double bond and a single bond going to it. So we would just have that 4th bond going to hydrogen, which is just assumed to be there without actually being written. But we can see it a little bit better at the bottom. But that's going to be why we have sp2 hybridization, because we've got those 2 carbon atoms as well as the 3rd hydrogen, which means in each of these carbons, we're going to have an unhybridized p orbital. But instead of having them overlap like we see with these first 2 images, where it's showing actual double bonds, single, double, single, kind of having them repeating, what we're going to see is, again, delocalized electrons, because we're going to see total overlap between all of those p orbitals. And again, that's going to be why the electrons in benzene are going to be delocalized. And we're not actually going to have single bond, double bond. We're really going to kind of think of these as 1.5 bonds all the way around. And then because of that, it's going to make benzene extremely, extremely stable. Or maybe not extremely stable, but more stable than you may expect with a ring structure like that. And then in addition to the orbital overlap, like we saw with the previous structures, What we can also do is use what's known as molecular orbital theory to get an understanding of what's sort of happening here, and then why some substances will actually form bonds and others won't. And with it, just before we kind of get ahead, you'll notice in this case, so these are two hydrogen atoms, and then we've got the molecular orbital. So now it's going to show the electrons being shared within the hydrogen molecule. So when we actually have them combine, what we're going to see is that there's going to be bonding and anti-bonding orbitals. And with it, we're going to think about electrons as waves with this idea. So with the bonding orbitals, in this case, this would be a sigma 1s bonding orbital. The waves are going to work constructively, meaning that they're going to add together. And this is going to lower the energy, whereas the anti-bonding ones are just going to be the opposite. They're going to be destructive. And that's why they're going to be higher energy here. And then we note the anti-bonding ones with just the little asterisk. So if we look at hydrogen, we can see why hydrogen is going to form a diatomic molecule, because we have, as the individual atoms, just a single 1s electron. But when we have these atoms combined to form the molecule, now we have both of those electrons fill in the sigma 1s orbital. And this is going to be a bonding orbital versus the anti-bonding orbital. So we can look at what's known as bond order, which is going to be half of the difference between bonding electrons and anti-bonding ones. So for hydrogen, we've got two bonding electrons. We've got zero anti-bonding electrons. So 1/2 of the difference of two just gives us one. And that's going to be why hydrogen actually just forms a single bond there. We'll see in a little bit bond orders of 2 and 3 in things like oxygen and nitrogen. But since hydrogen has a bond order of 1, that's why we're going to see the hydrogen molecule just has that single bond there. But now if we look at something like helium, where the 1s orbital in each case is completely filled, now when we look at the diatomic helium molecule, we can actually see why this isn't going to form. Because we, just like with Hund's rule, when we're looking at traditional orbital diagrams, we fill from lowest energy to highest. We do the same thing here. So we add our first 2 electrons. We've got 4 in total now. The first 2 go into this bonding orbital, but then the next 2 go into an anti-bonding orbital. So when we look at the bond order, half of the difference of 2 bonding electrons minus 2 anti-bonding, so half of 0, because it's 2 minus 2, just gives us 0. And that's going to be why helium isn't actually going to form this diatomic molecule. The bond order of 0 means there's not actually a bond being formed there. And that's why we would just have these 2 atoms stay separate. Whereas if we go back to helium, we actually have these 2 atoms combined to give us this hydrogen diatomic molecule there. And then with when we get into S and P orbitals, when we got the both of them there, we're going to see kind of the same thing we did before, where head-to-head overlap, or they're calling it end-on overlap here, is going to be our sigma. And then when we've got the sideways or the side-to-side overlap, that's going to be where we have the pi. But again, we'll have bonding. And then with the asterisk, we'll have the anti-bonding being the higher energy ones there. So you can see kind of similar to what we saw with hydrogen and helium. This one's just going to be, now we're looking at elements in the second period. So with the 2s, essentially the same as we saw with the 1s. It's just going to be a higher energy. 1s would just be down here. We still have sigma and then anti-bonding. But when we get to the p, now we've got 3 orbitals for each of them. So you can see we wind up with 6 orbitals in total. The first 3 are going to be bonding orbitals. So sigma and then 2 pi orbitals. And then we have the anti-bonding there. But what we will see in some cases is, if we go back for a second, so you can see with the 2p, we've got sigma, then 2 pi, and then we have the anti-bonding for pi and sigma. What we'll see with some of these elements, so things like boron, carbon, nitrogen, is the sigma sigma 2p bonding orbital is actually going to wind up being a higher energy than the pi 2p bonding orbital. And the reason for that is just going to be because there's going to be a more interaction between the s and the p orbitals. So we just see those flip with things like boron, carbon, and nitrogen. But if we continue through, we can look at, just for this final slide, we can see a few examples of these molecular orbital diagrams. And then we can get an understanding, again, of why these substances are going to form the diatomic molecules that they will. So if we look at, for instance, neon, neon 2. So remember, neon's a halogen all the way in group 18, all the way to the right side of the periodic table. We can see it's going to have a bond order of 0, because just like helium, this substance actually isn't going to form. And the reason for it is we have just as many bonding electrons as we have anti-bonding electrons. So if we look, we've got 2 bonding, 4 bonding, 8 bonding. Let me just add those up. But we've also got 8 anti-bonding. So half of 8 minus 8, just going to give us 0. So just like helium, we won't actually see this neon diatomic molecule form. But when we move to fluorine, if you think about it, each fluorine atom is going to have 1 less electron than the neon will. So if we've got 2 total, we should have 2 electrons less. So that's why we're just missing this top anti-bonding orbital. So now in the case of fluorine, what we're going to see is I don't want that thickness. We're going to see 2, 4, 8 bonding minus 4, 5, and 6. So we wind up with 2, but we take half of that, so it's really 1. And that's why we've got a bond order of 1 here. That's why if we look at fluorine, the molecule there, it's just going to have that single bond. Continue even further, oxygen lost 2 more anti-bonding. So it only has 4. Again, you can just see the difference here. It's not doubly occupied in the anti-bonding for the pi 2p. So because that 8 minus 4 gives us 4, but take half of it gives us 2. That's our bond order. That's why oxygen is going to be a double bond. And then the same thing with nitrogen. Now we got rid of all of these anti-bonding orbitals in the 2p, or anti-bonding electrons in the 2p, I should say. So now we just have that sigma 2s anti-bonding one. So 8 minus 2 gives us 6, but take half of it, bond order of 3. That's why we see a triple bond here. And then with this as well, we can look to see, so if you focus on the bond length, you can also see that kind of makes sense. So single bond, double bond, triple bond, we see the bond length decrease. And then as we go from triple bond, double bond, single bond, we see it increase again. So remember, as we have multiple bonds, those electrons or those atoms are going to be pulled a little bit closer than they would be if it was a single bond. But also, if you look, we've got this term magnetic behavior. And you may be able to notice, if you look, boron and oxygen are both going to be paramagnetic, while the other 3 here, we're excluding neon just because it's not actually going to form this molecule. That's why it doesn't actually have any properties here, just because it's going to have a 0 bond, meaning that these 2 are just going to stay as atoms. But if you look at oxygen and boron, what you may notice is that in each case, we've got unpaired electrons. And that's going to be what ultimately determines if it's paramagnetic or not. If we do have those unpaired electrons, the unpaired electrons here and here are going to wind up making it paramagnetic. And then with these para ones, what we're going to see is that means that they're going to be attracted to a magnetic field, where the diamagnetic is going to be slightly repelled by a magnetic field. But with these molecular orbital diagrams, that'll be kind of where we wrap it up for chapter 8.